Have you ever stopped to think about how much free storage Google is just giving out? Every time you sign up for a Gmail account, they give you 15 gigabytes of it completely for free. It doesn't sound like a lot until you realize there's almost 2 billion people with this 15 gigabytes of free storage, which means Google is now maintaining 30 billion gigabytes of storage free of charge to the world. And having to handle that and YouTube and Google Photos and everything else, has Google almost ever ran out of space? Is it? Yes. In the early days, Google relied on the Google File System, or GFS, one of its first large-scale storage solutions. GFS was designed to handle massive files, often several gigabytes or even terabytes in size, by distributing them across multiple machines. It was optimized for large read and write operations and built with fault tolerance in mind. But as Google's data needs skyrocketed, GFS eventually hit its limits. Enter Colossus, the next-generation file system that took over where GFS left off, bringing improved scalability and efficiency. Alongside Colossus, Bigtable was introduced, Google's powerful distributed database system designed to handle structured data at an enormous scale. Together, these two systems became the backbone of Google's storage and infrastructure. However, not all data fits neatly into these systems. For more transactional and relational workloads, Google turned to Cloud Spanner. Cloud Spanner plays a critical role in handling a significant portion of Google's cloud-based storage, ensuring high availability and consistency across the globe. How Google stores this virtually unlimited amount of data onto Cloud Spanner is complicated, so hold on to your hats. Cloud Spanner is a globally distributed, strongly consistent, and relational database that combines the scalability of NoSQL systems with the transactional guarantees of traditional SQL databases. It replicates data across multiple geographically dispersed data centers using synchronous replication protocols, ensuring high availability and fault tolerance. At its core lies the True Time API, a globally synchronized clock to provide bounded time uncertainty. This mechanism allows Cloud Spanner to order transactions accurately across distributed nodes and maintain external consistency. Google's storage system doesn't just throw data into a single repository. Instead, it partitions data into smaller units called splits, which are distributed across servers in a shared architecture. This approach ensures load balancing and enables horizontal scalability, allowing Google to efficiently manage vast amounts of data. However, handling transactions across multiple distributed servers presents significant challenges. In a distributed system, data is spread across numerous nodes, often located in different regions. When multiple transactions occur simultaneously, making sure that each one is executed in the correct order without conflicts becomes increasingly difficult. Inconsistencies can arise if one server processes a write operation while another reads outdated data, leading to race conditions, lost updates, or write skew. This is where Cloud Spanner comes in. It uses a two-phase commit protocol combined with multi-version concurrency control, or MVCC, to enforce ACID properties, ensuring reliability and consistency at a global scale. A transaction in Cloud Spanner is atomic, meaning it either executes completely or is fully rolled back. There's no partial execution that could leave the system in an inconsistent state. These transactions are isolated, preventing concurrent operations from interfering with each other, and once committed, they persist even in the event of a system failure. Using Google's True Time API, Google can synchronize operations across data centers worldwide. This guarantees external consistency, where transactions are executed in a globally consistent order, preventing anomalies such as write skew. By integrating sharding, strong consistency, and global distribution, Cloud Spanner provides a scalable, fault-tolerant, and high-performance relational database solution, capable of handling Google's immense data workloads while maintaining strict transactional guarantees. And that's why Google relies on it. Because when you're running a system that needs to process billions of transactions across the world, you can't afford to have things breaking left and right. But this doesn't explain all the data Google has to pull in real time, like with its two biggest functions, Google Maps and Google Search. Speaking of, thanks so much for all the support on the channel lately. It really means a lot, and I want to give something back to you guys. So do you need a job? That sounded a bit weird. But whether you're a UX designer, app developer, freelancer, or just a curious viewer, I want to get to know you guys, share some UX and UI tips, and maybe even get a gig. So I made a Discord channel for us and want to make this the place to be for front-end professionals. And I'm having talks with people to get some employers in there so you can connect with them too and find some jobs in the future. I'm really excited to get this thing started, so I hope you'll join me. While Cloud Spanner manages globally distributed nodes, Google Maps and Google Search require a distinct architecture to handle real-time data ingestion and synchronization. For these high-demand systems, Google uses robust messaging frameworks such as Apache Kafka and Google Cloud Pub or Sub. Apache Kafka is a distributed streaming platform designed for real-time event processing. It decouples data producers from consumers by employing a publish-subscribe model backed by a durable, partitioned, and replicated log. This log-based approach enables efficient event replay and stateful stream processing, ensuring that large volumes of events, ranging from user queries to dynamic location updates, are processed with minimal latency. In parallel, Google Cloud Pub or Sub serves as a globally scalable messaging service that facilitates asynchronous communication among microservices. It supports flexible delivery semantics, including at least once and exactly once processing, to guarantee reliable event propagation. Together, these frameworks empower Google's systems to ingest, distribute, and synchronize real-time data across multiple regions, ensuring rapid updates and maintaining high system responsiveness even under significant load. This intricate orchestration of streaming technologies is vital for sustaining the dynamic and interactive nature of Google's core services. These sophisticated real-time pipelines are crucial for maintaining the responsiveness and scalability of global applications. At the heart of this processing architecture lies MapReduce, a fault-tolerant distributed computing paradigm designed for massive data analytics. MapReduce decomposes vast datasets into discrete, manageable tasks via a map function, which is executed in parallel across a cluster's nodes. Each node processes its partition of the data independently, producing intermediate key-value pairs that are then shuffled and aggregated by a reduce function. This multi-stage process not only ensures parallelism and load balancing, but also optimizes resource utilization and minimizes network bottlenecks. Together, Cloud Spanner's robust storage capabilities and MapReduce's scalable parallel processing framework form the backbone of Google's data processing ecosystem, empowering the company to deliver real-time, data-driven insights at global scale. Building on the sophisticated real-time messaging and processing frameworks, the cumulative data generated by Google's services was just too much for Google to handle. Every search query, email, YouTube view, and navigation request is logged, processed, and stored, contributing to an exponentially growing digital footprint. For instance, in 2020 alone, Google's infrastructure handled over 40,000 search queries per second through a highly optimized distributed system that minimizes latency and maximizes throughput. With the rise of AI models that generate massive volumes of data and users uploading an estimated 720,000 hours of YouTube content daily, the volume of information rapidly escalates, pressuring storage architectures to scale further. From a technical perspective, the data generated is funneled through intricate pipelines involving distributed file systems, shared databases, and robust indexing algorithms that ensure swift retrieval and real-time analysis. Each data center in Google's global network, now exceeding 20 facilities, employs advanced cooling, high-speed interconnects, and redundant systems to guarantee fault tolerance and continuous operation. These facilities represent billions in capital expenditures, or CapEx, with operational costs continually rising to meet the demands of such massive data ingestion and processing. The finances are something else entirely. Google's business model, which underpins free services like Gmail, Gmail, Google Photos, and Google Drive through advertising revenue and paid tiers is increasingly strained by these infrastructure demands. Historically, Google Photos offered unlimited free storage, but in 2021, this policy was revised as the sheer volume of user-generated content, images, selfies, screenshots, and videos became unsustainable. The same trend now affects Google Drive and Gmail, where unlimited storage has given way to tiered storage limits and monetization strategies. So Google is definitely running out of storage. It's just a matter of when the systems I explained in this video finally buckle under the pressure.